Hi all, welcome to part 8 combination circuits. See what we discussed so far is regarding different combination circuit. Particularly we saw that adder circuit, half adder, full adder, ripple carry adder, that carry look ahead adder, right? So these are all the things we discussed so far. Now regarding the topic that is coming next is a binary subtractor circuit. So it's more than calling it as a subtractor, this is something that can perform both addition and subtraction. So the adder circuit only I am modifying like this, so I can call it as a binary adder bar subtractor circuit. So that is what we are going to see. Okay, so it can do both addition and subtraction. So you can see that this is just looking like a, so in ripple carry adder, what happened is like some set of full adders you connected, right? It's the first full adder, second full adder, like that. The full adder is going to take the inputs, the particular ith bits, and it's going to add, and some will be generated, carry will be given to the next full adder, like that. So that circuit only, but in addition to that we are depending some XOR gates, and we are doing something there. So to explain this concept, first I have to make clear that whether you know the subtraction process, this is something you are supposed to study in your uh, first module, right? So what is happening in subtraction? Suppose I want to subtract b from a, right? So this b is supposed to be subtracted from a, and how can you visualize this subtraction as an addition? So what you can do is you can do like a plus minus b, something like this. So both are same, right? So now what I'm doing is I'm taking the representation to the 2's complement or 1's complement, anything you can depend to represent the negative number. So if that is the case, you know how to represent this positive number in 2's complement, as well as how to represent a negative number in 2's complement. Then you do the normal addition of 2's complement binary numbers, you will get the answer. So but you have to depend on, so to do like this, so how will you represent this negative number? Use 1's complement arithmetic or 2's complement arithmetic. A sign magnitude is also there, but typically for so this is advanced, and you know the negative side of the sign magnitude representation, everything, right? So mainly in computers, again this compared to 1's complement, also this 2's complement is having advantage. So I'm now discussing the benefits of, so this is something you are supposed to know from your concept, like representation of the negative number, and that time you are supposed to know this. But right now I hope that you know it, right? So what makes this 2's complement special? So we are just focusing on this one. So this is important for us. So by default in computer memory, everywhere negative numbers are represented by 2's complement. Actually we have three ways, like sign magnitude is one way, 1's complement, 2's complement, but out of them the 2's complement is having some extra benefits over the other two. If you don't know, you just try to understand what it is, because you are supposed to know it right now. Okay, so that what makes this 2's complement different, and with that something like the unique representation of 0 and something else, right? Hope you remember. Yeah, that's all. And if that is the case, how can you do this? Suppose I have the first number as 1106, say, and the second number is like this is what I have to subtract, say, let me take a bigger number, 0 1 1 1, and you know when you are subtracting these two, the result has to be, let me just take an example, this is your 6, right? This is your 7. So when you are subtracting these two, you will get something like a -1. So you should get the representation of -1 as the answer. We assume that everywhere we are using 2's complement. If that is the case, what you will do? First you will take a as it is. So a you will take like a 0 1 1 0. Then you will take a 2's complement representation of b. Why I'm not taking 2's complement representation of a? By default positive number is represented as it is in 2's complement, right? So in 2's complement, so okay, let me write 2's complement representation of a, that is as it is, because it's a positive number. But for b, what I need is 2's complement representation of minus b I want, right? Because I'm trying to do a minus b. So instead of doing a minus b, what I am trying to do is a plus minus b, something like this. So for minus b and a, 2's complement representation I am depending, then I am adding. So that is the process. So how will you represent this 2's minus 7, something like that? So you are going to do 6 minus 7. So what you do in the background, 6 plus minus 7. So what is the 2's complement representation of minus 7? That is my question. This is your plus 7, and for minus 7 you have to take the 2's complement, right? So you will get something like a and I'm going again, I'm not repeating how this 2's complement is to be taken, or simply I can tell like 1's complement plus 1. So take the 1's complement, you will get like 1 0 0 0 0, and plus 1 will give you this. Or there is a direct way also that you recollect how it is to be done. Fine. So this is the 2's complement representation of minus b. Once I am getting these two, I can do the normal addition. So 0 plus 1 1 1 1 1. So this is the answer I am getting. Right. So this is it correct answer? So now the system is 2's complement. So what is the number represented by 1 1 1 1 in 2's complement arithmetic? In 2's complement arithmetic, which is a number represented like this? So again, that is a different topic. So this is minus 1. Okay, so how this is minus 1, if somebody don't know about this representation 2's complement, see 2's complement, the concept of 2's complement is very important for computer science students. If you are, somebody is having difficulty in it, you can tell me, I may take a different video for that. So right now, as I assume that you already know it. Okay, so with that I am proceeding. This continuous 1 is actually representation of minus 1. If at any point if you have any doubt, you can ask in the discussion class. I will clarify. Okay, I will either try to clarify, or if needed for majority of students, I will make a different video for it. Yeah, that's all. So you are getting the correct answer. So this is a procedure, right? So you have to take the 2's complement of the subtrahend, and you do addition with the other one, right? A minus b, take 2's complement of b and add with a. So that is the idea. Now how to get 2's complement? We have a shortcut and all, but the direct method is like take 1's complement and then add a 1. So how to get 1's complement? Flip all the bits, right? So this one, everything you have to flip, and then finally you will add a 1. So the thing is that, so this is a circuit, just observe the circuit. So here this is something like a I can say that it is a mod bit. So typically let me call it as a mod bit. So what it is doing, it is actually controlling whether you have to perform addition or subtraction. See, m is equal to 0, it will behave like a adder. So it will be a adder, a pure adder, the normal ripple carry adder you will get. Now when m is equal to 1, you will get a subtractor. So that is the idea. Whether it is doing addition or subtraction for you, that is dependent on this value of n. Yes. So mod bit is equal to 0 means it will work like an adder. It's equal to 1 means subtractor. So we can see that. So when m is equal to 0, what will happen? You can see that this m bit is given to all the XOR gates. So here you can see we have two number. Which are to be either I want to do addition or subtraction, that I don't know. 4 bit, right? So A0, A1, A2, A3 is the first one. Then B0, B1, B2, B3 is the second one. Now when you are performing addition of these two, see the first one, there is no change, right? Whether it is addition or subtraction, the A0, A1, A2, A3, they are to be given to the adder as it is. So A0, A1, you can see, right? So these bits are directly given to the adder, right? Those bits are directly given to the adder. Now what you have to do with the second bit is, I mean this B0, B1, B2, B3, so they have to be given as it is when this mod bit is equal to 0. So when this, so first we are going to give to this B0, B1, B2, B3 etc. through a XOR gate. So here we have a XOR gate, and hope you remember how this XOR gate is working. The truth table of XOR gate, let me tell you, A, B, A XOR B, right? So how many of you remember the truth table? 0 0 0 1 1 0 1 1, and when both the inputs are same, it's going to give you a 0, and when I'm getting something like, it's going to give you a 1. Now observe very clearly this XOR gate. So when one of the input of this XOR gate is 0, so just look at the first row. When one of the input of the XOR gate is 0, the other input is coming to the output as it is, right? When one of the input of the XOR gate is 0, so 0 is something like the other input, it's like an identity, right? So what is the B? That will come as output when A is 0. So when A is 0, B will come as output, right? So XOR gate. Then when this mod bit is equal to 0, mod bit is equal to 0 means here you are getting a 0. Here also you are getting a 0. Here also you are getting a 0. Here also you are getting a 0. Mod bit is equal to 0 means, okay. And that time what is in B0? If B0 is 1, output will be 1. If B0 is 0, output will be 0. Is it clear? So this B0 will come as it is without any change. Similarly everywhere. So hope it is clear. I am removing this. That's all. So that is the first observation. So when mod bit is equal to 0, it will work like an adder because there is no change. Just the normal ripple carry adder. Hope you remember the full adder circuit is what we are having. The carry you are giving to the full adders, that is following them. So something like that. Yeah. And the two inputs you are applying like A0, B0. Just do the addition. This will work and it will generate S0. Then it will generate the carry. And this A1. Here it is 0. B1 you will feed here because there is no change for A1, B1. When M is equal to 0, this will come as it is. There is no change. This B1, whether it is 1, B1 will come. If it is 0, 0 will come, like that. Similarly, this B2, A2. So like that, it will just perform like a normal adder. Now, when I am having mod bit is equal to 1. When mod bit is equal to 1, this is again very, very important observation. See what is happening when mod bit is equal to 1. When mod bit is equal to 1, this is what is happening. Let me use a different color. Yeah. So this is the thing. When one of the input is 1, what is here? It's getting complemented. The 0 is getting 1. 1 is getting 0, right? So just you are getting the complement. So this is very important. You can use this XOR gate for complementing something. Right. So complementing. So make sure that one of the input of the XOR gate is 1. When one of the input of the XOR gate is 1, right, what will happen? So what is here? B0 is here. B0 can be 1 or 0, whatever it is. When one input is 1, if B0 is 0, this XOR gate is going to give you 1, or B0 complement will come here. Similarly, when this mod bit is equal to 1, B1, here you will get B1 complement. Means if this B1 is equal to 0, you will get 1. If this is equal to 1, you will get 0, like that. Similarly, when mod is equal to 1, this B2 you will get its complement, B2 complement. When mod is equal to 1, you will get, when this mod bit is equal to 1, this B3, its complement will be coming here. That's all. So you are getting the complement, means this 1 and 0 they are changed, means you are getting the ones complement only. But for subtraction, you can do subtraction using ones complement also fine. But standard implementation, we need a 2's complement for performing subtraction, right? So that is a standard implementation. And that time what you have to do is like this M bit itself you are giving to the C0 is also, because in a typical add the C0 is found to be 0 because it's the least significant position. Addition, I don't have to take a carry further. But when it comes to subtraction, this M is equal to 1, right? So when it comes to subtraction, so here I am showing highlighting subtraction. So when it is when this M is equal to 1, that is what I am highlighted in the figure. This carry bit will be 1. That means in addition to the 1's complement, I am adding a 1 also. So 1's complement plus 1. This least significant carry is going to be added with the whole thing, right? So 1's complement plus 1 is going to give me a 2's complement. So on the background, what is happening is the A0, A1, A2, I am taking as it is. This A0 is coming, A1 is coming, A2 is coming, and A3 is coming. And for A3 is coming. B0, B1, B2, B3, I am taking their complement, right? So I am adding. So 1's complement addition is happened actually, but with this C0 is equal to 1. 1's complement plus 1 is actually 2's complement. So the 2's complement addition happened. Is it clear? So that's also, in that way you are getting the sum bits. Now what about the final carry and all? So here they are showing something extra in the figure. So this is very interesting, but I am not going to explain it here. You can this is something you are supposed to know again from the number theory. If you don't know, if needed, I will explain at this point. So let me just tell you what it is. It is something called overflow. Overflow. I don't know how many of you the concept of overflow is clear, or try to spend your own time to understand what is overflow. First you understand that this is not something carry and overflow both are entirely different concept. But if I want to explain this, I just need some half an hour to explain what is overflow. So I am just telling you this is overflow, and one way of detecting overflow is actually implemented. So for any two number, when you are performing addition or subtraction, whether there is overflow or not, you can simply detect by using an XOR gate. Again, XOR gate, another application. Take tons complement, the subtraction logic, overflow, everywhere you are using this, right? It's very handy. If you are not having XOR gate directly with you, you have to implement using the and over realization. See how important it is, right? And again, we will see many applications of this XOR gate, right? Yeah, here also you are using an XOR gate. So the most significant, the final carry is your C4, right? So this is not your overflow, and this carry and the carry coming to the most significant position, say C3, if both of them are different, then there is an overflow. If these two bits are different, then XOR gate is going to give you a 1. So accordingly you can dictate. So V is equal to 1 means there is overflow. Okay. So what I was trying to say, in general, when you are trying to add something like an minus 1, an minus 2, etc., a0, b0, etc., bn minus 2 and bn is 2 n bit number you are trying to add, right? And you know, when you are adding, you will get some bits like s0, s1, etc., some Sn minus 2 and Sn minus 1, and finally from this position. So what is the carry coming to this position? Typically we denote, hope you remember, here the carry input to carry, let it be C0, so that the carry coming to this position is Cn minus 1, and the carry coming out from this position, the final one, this is your Cn. So that is the last bit of the sum also, Cn and Cn minus 1. So Cn minus 1 is a carry that is coming from here to here, and the carry leaving from here to here is your Cn. Right. So Cn minus 1 and Cn. So I can say that there is overflow. So when you perform Cn XOR Cn minus 1, if you are getting a 1, that means there is overflow. There is overflow. Why it is? There is a reason that you can try spend your own time. If you find it difficult to understand, I will explain for sure. First you make an attempt by yourself. Try to understand what is overflow and why I am getting an overflow when this XOR operation is going. So when this carry come into the most significant position and the carry leaving from the most significant position, if they are different, there is overflow. If they are same, there is no overflow. Why it is so? You try to understand yourself. So anyway, this circuit is detecting overflow as well as, and it can perform addition, subtraction as guided by this m. So the m is equal to 1, it will perform as a subtractor. M is equal to 0, it will perform as a adder. Right? Very important concept. So this is your binary adder bar subtractor circuit. So thanks for watching.